All right. So the current and power has to travel along the lines to the load. All right. I'll move that back up here. Yeah. All right. So yes. So there are lines. I don't remember if this was a three-phase four-wire system. I would have to look back at the question. All right. Let me just look back at it quickly.
The three phase.
Four-wire.
Yeah.
All right. Three-phase 400 volt has a load connected in star. All right. So it didn't really tell you whether or not it was three-phase four-wire, but let's assume that it was three-phase four-wire. All right. So this diagram could help too, So if you imagine this, so imagine the source is over here now, right? Imagine the source is on your right, and then currents now are gonna be coming from the source along the lines, right? And travel through each of the phases, through the impedance which are in the phases. So in the first one, say that again?
I'm saying I get that part of the concept. It's just a confusion I had with the 400 volt as being the line voltage. I was wondering, if because I got line voltage to be the voltage between any two particular lines.
Right, any two. So you look, there are going to be three combinations of two lines, right?
Yeah.
So there is one between the red and the yellow. There's one between the yellow and the blue, and there's one between the blue and the red.
Oh, so all of them is 400. All of them are 400.
Yeah, all of them have a magnitude of 400.
Oh, even though it's unbalanced.
Yeah. All right. I suspect that maybe you're missing the notes, and maybe that is part of the challenge. All right, but as I will get to you before we can get it to everybody with the notes. All right. But one of the statements that we made was that I'm trying to find it now. That all of, in this problem in this course, the phase voltage phasors, see it here, the phase voltage phasors and the line voltage phasors will be considered to be balanced. All right. So no matter how the system is unbalanced, that is so I make a little sub note there. That is even if the loads are not balanced, the voltages are considered to be balanced.
Yeah.
All right. And I made the point that when you get to um, electrical power systems, you will experience voltages that are unbalanced, right? So you will have both balanced and unbalanced systems, right? Usually, unbalance comes about when there's a fault, right? Or if the loads are in, like in our cases now, when the loads are different in each phase. So, but we are considering that our voltage is always balanced. When you get to power systems, you will look at voltages that are not, in some cases, not balanced. All right. All right. So is that clear? So the voltages are going to have the same magnitude, and they are going to be at angles like we calculated. We calculated some angles yesterday. Um, Where were they? Right. So one was at 150, one was at 270, and one was at 30. All right. So that's what the line voltage is. But you're not too much interested in solving for the line voltages. No, you're asked to find the current in each phase, right? Or in each line. You with me?
Yes, sir.
Right. So you're asked to find the phase current, so which is the current going down here. So that means that you need phase voltage based on what we did yesterday. All right. But when I send you the notes and you read over, I believe you will get a better um, picture of how we approach the thing. All right. I think I heard Mr. Campbell say that he was okay with it.
Yes, sir.
Oh, okay. Okay. All right. That's good. Um, Anybody else had any challenge? All right. So we're gonna um, tackle today's.
Um,
Yeah. Go ahead.
Sir, I had a little challenge with the neutral current, but I figure it was because I had the wrong angles and the current, the magnitudes of the current.
Okay. Well. All right. So you had seen the answers for I had put all the answers. Don't know if you had written them
Yes,
down.
sir. I saw it after, but um, I was just working it out before. Um, I look at the answers, but I know what the answer was.
Okay. All right. Yeah. When you read over the notes and look in the textbooks, I think you will, be more comfortable with what we have done. All right. So I'm not very concerned now since you have not gotten a chance to read over the thing. But by next week, I would expect that everybody would be on top of their game. All right. All right. So let me can all right, close minimize this. Yeah. Or new share. So this is the one that we'll be looking at today. So you'll be working out these questions. So I will give you let's say about um, 10 minutes to do question one, and then we can come back and look at it. It should be fairly easy. So I'm gonna give you 10 minutes to do the question one, and then we can come back and look at the solution. Right now, I will leave it up there. I had sent it out in the email not too long ago, so hopefully you have downloaded it also. All right, so everybody know what to do. We have for question one, you're gonna solve this. I'm giving you about 10 minutes to do it. So by about 5:25, we can look back at it. So the question says that 320 microfarad capacitors are star connected across a 400 volt 50 hertz three phase three wire supply, and we should calculate the current in each line. All right, so can go ahead and do that. Just use the same procedures that we have been doing before. There's just a little added dimension to this one, but let's see how you figure it out. All right. Oh, this is IB. This last one here is IB.
Problem for me.
The angle is the problem.
I get the value, I get the magnitude, but the angle.
Yes, sir. Same, sir. With the problem, sir.
Oh, oh, but why? Why is the angle the problem?
Sir, I don't know how to approach it to the
Let's
angle.
so
I
let's
don't know,
let's
I guess I'm
all right. Let's go through the solution. Put this a little bit
So
over
question
here.
before
All
we
right. So
start going through the answers.
yeah.
I recall yesterday in the class you mentioned that when you use a calculator you might get a negative angle, but it might be the correct answer. Is it a case where you're supposed to like positive part because I got negative?
Oh well, yeah. All right. So what you should do when you see you get a negative number, basically what you can do is take that negative angle from 360, and you will see whether or not it ends up back with the answers that I
Alright.
have. So if you get a 150, take that from 360, and you should end up with what?
210.
210, right? And if you get a negative 30, you just add that to the 360. All right. So any negative number you get to just add it to 360, and it should get you to the positive answer. Because remember, the negative is going in the opposite direction um, to how the phasors should operate, or how the phasors normally rotate. All right. So it sounds like you're on the right track then. All right. So let me bring up.
Sir, quick question, sir.
Yeah.
When you're working these out, we should have the calculator and radians.
No, no, no.
Okay.
Degrees.
Okay.
All right. So all right. So this is the approach to it, right? They said that this was a three-phase, three-wire supply. All right. So so now this is my source, my voltage source, three-phase, 400 volts, 50 hertz supply. All right. and it's a three-phase, three-wire supply, right? But the load is connected in star, so the star connection of the three capacitors here, right? We know that the line voltage, so the voltage between any two lines is 400 volts, and we need a phase voltage. We need the phase voltage, so we can calculate the phase voltage from the formula V phase equal to VL over root 3. All right. And this is 230.94 volts, right? So the phase voltage is that. Now, then we need now to define our phasors. And remember, our red phase is always at angle 0. The yellow phase is at 240. And the blue phase is at 120. For the sequence in which we are operating, right? We're operating the red, yellow, blue sequence. I will speak more about that during the next class. But, right, so, but I showed you how the phasors were rotating lines. Right, so, all right. So those, right, so we want to find the current on those lines, in those lines. So that's the question. To find the line current. All right, but remember, for a star system, look, the line current is also the phase current, right? So before we can find the line stars, before we can find,
Yes.
all right, so line current, you must find the phase current. All right. So we find to find the phase current now, then we need the phase voltages. So we have defined that these are how our voltage phases are going to be located, right? VR is going to be at angle 0, VY is at 240, and VB is at 120. And this is a standard thing, so I didn't just arbitrarily choose it. But this is the um, phase sequence that we operate in red, yellow, blue. So to find the current, we need to find its impedance, right? Or its capacitive reactance. To find an XC is equal to 159.155 ohms. All right. But capacitance, the capacity reactance is also a phasor, and it is at angle minus 90 degrees, right? So when we find in the red phase current now is the red phase voltage divided by the impedance in the red phase. So the impedance is the same in each of the phases because all of them are 20 microfarad, right? So we know the impedance is the same in each phase. So VR is 230.94 at angle 0. Yeah, sorry, go ahead.
Quick question. So for the capacitive reactance, sir, because the current is leading the voltage by 90 degrees, sir, and it's current with respect to voltage, and because you're moving clockwise, that's why you have a negative 90.
Right, right. The impedance itself. So the impedance will be lagging. Will be at 90 minus 90 degrees, right? The impedance itself, the angle for the capacitance. All right, and that will work out now to give you a leading current when you divide the voltage by the capacitance, the capacitive reactance. You will now end up with a leading current. So you will notice now that IR is leading VR by 90 degrees.
Okay,
Right?
all right, sir. All right, sir.
Right. So the capacitor will cause a leading power factor, or cause the current to lead the voltage.
All right, sir.
All right, for the particular phase that it is in. All right, and so you will see the same thing for each of them. For each of them, the current is leading the voltage by 90 degrees.
All right, sir.
So Vy is 230.94 angle 240. We divide that by Zy, and we end up with 1.451 at angle 330. And similarly for IB, you add the 90 to the 120, you get 210. All right.
Sir.
Yes.
All right. You see what you have there as in term, not the answer part, the 230.94 over the 1.59. I have all of that, but I got the current for IR, but for the other two, I'm getting 0.577 for the magnitude. Right?
No, man, but it's the same voltage.
Yes.
So no, look and see if your mode or your calculator has changed.
Let me try. Let me see.
Or probably it's in rectangular form.
Yeah, I changed it to the polar, and that's what I'm getting still.
What kind of calculator you have? The Casio FX115
Well,
ES?
actually, I'm using the one on my phone.
Oh, it has the it has sign.
One. Yeah.
Oh, complex
Complex
numbers.
and all of that. Yes, sir.
Oh, then how? I mean, is the same magnitude will be there because you're dividing two. If you just look about the magnitude part alone, it's 230.94 divided by 159.155.
Yes.
So that the magnitude part should be the same, and then the angles now. When you're dividing, you subtract angles, right?
Yes, sir.
0 minus minus 90 give you 90, and 240 minus minus 90 give you 330. I mean, it minus and minus give you plus, right? So you end up adding them.
I'm
All
going
right.
to try with the actual calculator and see, because maybe it's the circuitry in the phone.
Yeah, could be.
All right.
All right. So everybody okay with this now then? At least you see the approach. It's fairly straightforward. All right. Question 2, kind of similar, but it now has a resistance and an inductance. All right. So we have 3 inductors connected in star, but the inductors in of themselves now have a resistance of 10 ohm and an inductance of 0.019 Henry. And again, now you're asked to find the line current and the power factor. All right. So since you had 10 minutes to do that one, let's see if you can do this one in 10 minutes. So, or less because what you see when the system is let me give you a hint. When the system is balanced, you only really need to find what is happening in one phase. So if the loads are the same in each of the phases, you only really need to find what's happening in one phase. Because the only thing will happen now is that the angles for the current will be different, but the magnitude is going to be the same. So you only really need to know what's happening in one phase if the system is balanced, and then you can take it from there. So this one I had done what they had asked. They said calculate the current in each line. But this one now, the second one, they just say find the value of the line current, which means you only need one, right? Because since the system is balanced, the same magnitude will be in each phase. So,
Sir.
Go ahead and
So it says line current. Go down. Let me see it again. Value of the line current. So you don't want
man. Yeah. So remember, the line current is a phasor, so it has magnitude and angle. Some books actually not give you the angle, but I think is a more complete answer when you have both magnitude and angle. Since it's a phasor, and you might be asked to draw phasor diagrams too, so you better know where the phasor is located. All right. So if they had specified find the magnitude of the line current only, then you wouldn't need to find the angle. But since they didn't specify that, you find both. All right. So another 10 minutes. Us whether or not it was a three phase, but it probably didn't really matter
Yes, sir.
Yes, sir.
since we weren't asked to find neutral current or anything like that. In terms of the actual working out, we still needed to find phase voltage and things. Inductors, so each of them were 10 ohm and had an find the inductive reactance and the
So, excuse me, come on, it's bigger. I'm gonna see. Oh, okay, never mind.
all right. Um, So, right. So we need to find the inductive reactance, and that is XL, and it's equal to 2 pi f L. So work out what XL is equal to, and then we need now to find that impedance of each inductor. So you use this R plus JXL, or you could do your triangle and use Pythagoras. Um, but your calculator can do this easily, complex numbers. So it's fairly simple to do that, and Z works out to be 11.646 at angle 30.83 ohms, right? And I drew the triangle here so that you would get a picture of what it looks like. All right, so this is XL, not XC, right? XL. And then we need, since we needed to find the current in each line, we need to find the phase current. And before we can find the phase current, we need the phase voltage. All right. And what I told you before, since we are, they asked us to find the line current. And since the system is balanced, we only really need to find one phase. So well, if you're going to use the red phase, you have to use the red phase voltage and the red phase impedance. All right. So the red phase voltage is 230.94 at angle 0. And IR then is VR over ZR. So the voltage across the red phase divided by the red phase impedance. That will be the current in the red phase. Once you find that phase current, you know that the phase current and the line current is the same. Right? So once you calculate the phase current for the star system, the line current and the phase current are the same. So we find for the red phase, so the current in the red phase is 19.83 at angle minus 30.83. So the same magnitude will be in the other two lines. It's just that the angles now is going to be 120 degrees ahead and behind this one. All right. And one way of finding the power factor is to find the power factor from this triangle. And power factor is cos theta, which will be the adjacent over the hypotenuse. But when you do this, you actually get the angle already. So it's really the cosine of this angle. All right. So the cosine of 30.83 is equal to that. You could also test it by finding cosine, finding R divided by Z, R divided by Z, and that should give you the value also. All right. This one is a little bit more complicated. The last one, the third one. So I am going to leave that for you to do for homework. Question 3. Right? And do it for homework. And if you get this answer, you can send it to me. So the answer is 17.32 at angle 124.16. It'll be very interesting to see you do this. And if you do this, if you can do this, then you would have understood how to deal with phasors, lagging and leading, and all of those kind of stuff. You would understand power factor. All right, so you don't have enough time to do it now. So I am going to say we can close now, and you try to do this, and you can send me, just scan your solution and send me, and I will take a look at it.
Sure.